This lesson will be about alternating series, and if you think about it, in the past few lessons, almost everything I've said or that we mentioned has been, as long as this is positive, and as long as both of these things are positive, we can compare them, and that sort of thing. So an alternating series will be the first time we delve into series that, well, aren't always positive. So an example of an alternating series is the alternating harmonic series. 1 minus a half plus a third minus a fourth. So you can see the harmonic series is the same thing, but plus, 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 and here we alternate between positive and negative. This could also be written as the sum negative 1 to the n minus 1 over n. Right? Those two are the same thing. Now there's an alternating series test to determine convergence, and it is as follows. If you, first of all, can express any alternating series like this, right? There's the alternating part, which is the negative 1 to the n minus 1, and this b sub n, that's the part that changes from one alternating series to the next. This really won't, except it could be n instead of n minus 1. In other words, instead of being positive, negative, positive, it could be negative, positive, negative, but it's really a pretty trivial difference. So, point being, you can write it as an alternating part of some other sequence or series b sub n. If two things are satisfied, if one, b sub n plus 1 is less than or equal to b sub n, which means the next term is always smaller than the one before it in your sequence, excluding the alternating part. And the second part is, not only does each one have to be smaller than the one before it, but they must go to 0 as well. So if you know those two things, then you know the series is convergent. One thing I should add to this statement right here is that this has to be true for all n. And of course, n is already a natural number, a positive integer. Okay, so let's get back to that harmonic one and apply this test. So we're going to check condition number 1. Is this true? Well, 1 over n plus 1 is less than 1 over n. Yep. Right? Bigger denominator, small. Condition number 2, take the limit as n approaches infinity of the b sub n's. It's pretty clear. 1, half, third, fourth, etc. That one goes to 0. So this series, the alternating harmonic series, is convergent. Which is a somewhat interesting result because the harmonic series itself was divergent. Okay, let's do another one. And as always, they'll get more interesting as we go. So we'll take this as our series. I already have it written the way we want it to be written. That doesn't necessarily make it easy. So we have two conditions, right? And I'm just going to go right to the second condition. If you take the limit as n approaches infinity of that, you get 3/4. So that tells us that we can't apply the alternating series test, right? That's not to say that immediately it's divergent. The alternating series test says, if this and this, then it's convergent. It doesn't mention the opposite, right? So it doesn't say, if it fails this and fails this, or one or the other, that it's automatically divergent. So we will also consider the fact, and this will kind of put the nail in the coffin, we'll consider the limit as n goes to infinity of this. Just think, oops, sorry. This limit actually doesn't exist. And if the limit of the sequence doesn't exist, well then remember, you're out of luck. Remember, the limit of the sequence that this whole series is based on must go to 0 for you to even have a chance of being convergent. This one doesn't, so it's divergent. Okay, and una más. Okay, now number 1 here, checking our 2 conditions. The first condition is not obvious. I just skipped this one because I knew that was the second condition was not going to work out here. Checking condition 1, though, is not always that simple. Remember, condition 1 was that the terms, each next term was smaller than the one before it. But I don't think everybody and their sister looks at that and says, yeah, of course, you know, this thing is going down, it's decreasing every time. So what we will actually do is we'll just consider that thing to be a function. And if you want to know if it decreases, and you know calculus, take its derivative. And why don't you do the derivative, hit pause, and then resume when you're finished. You should get this. That's f prime. And now if you set that equal to 0 and solve and look for when it's decreasing, it turns out that it's decreasing on the interval, the cube root of 2 to infinity. Okay? So if it's decreasing that whole time, then we're good, right? Remember, well, that's that. So that's the first condition. No need to go into more detail there. But if you're kind of wondering where the heck did that derivative come from, it comes from the fact that when I look at this, the alternating harmonic series, if you looked at the sequence, just the 1 over 1, 1 over 2, 1 over 3, very clear that that thing, that each next term is smaller than the one before it. That's not necessarily the case here. So if that's not the case, we just verified it via examination as a function. Now the next thing to take care of is the limit as n approaches infinity of that. And we know that we could divide through by n cubed if you wanted to, top and bottom. Also, we know that the denominator is dominant, which means this goes to 0, which means now the whole thing is convergent because of the alternating series test. So actually that's it. The alternating series test, you just need 2 things. You need to know that the next term every time is smaller than the term before it. And you also need to know that the limit of the sequence that's not the alternating part goes to 0. Okay?